For centuries, humanity has asked a simple question: why do things fall? It's a question we've all answered intuitively since childhood. You let go of an apple and it falls to the ground. But the nature of what makes it fall, that simple fact, leads us down one of the most profound revisions of scientific thought in history. Gravity is familiar. We live with it every day. Yet when we ask what gravity really is, physics takes us into realms that challenge intuition, logic, and even the nature of reality itself. Today, we'll take a journey from Newton's elegant laws through Einstein's revolution and into modern physics where gravity blurs into geometry and space-time. This isn't just physics. This is a story about reality itself. What if gravity isn't a force at all? That question might sound strange, but the answer reshapes how we understand the universe itself. In the late 17th century, Sir Isaac Newton offered the first universally successful description of gravity. His laws were simple, powerful, and predictive. Newton's law of universal gravitation states, "Every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them." Mathematically, F equals G times m1 m2 over r squared, where F is the gravitational force, m1 and m2 are the masses, r is the distance between them, g is the gravitational constant. This law explained why apples fall, why the moon orbits Earth, and why planets follow elliptical paths. Newton's genius was not only describing gravity, but showing that the same force governs both falling apples and planetary motion. This was a profound unification. In Newton's view, gravity is a force. It acts at a distance, and it pulls objects toward each other. Imagine this: two masses, unseen strings stretching between them, pulling inward. That's how Newton depicted gravity. This concept worked exceptionally well for over 200 years. It predicted orbital periods, tides, trajectories of comets, even the motion of Jupiter's moons. But there was a problem, a deep one. Newton himself was uneasy about how gravity worked. He wrote in a letter that one body may act upon another at a distance without anything mediating. Newton, 1692. It seemed to imply that changes in one mass affected another instantly, no matter the distance, without a medium. This was conceptually troubling because it suggested instantaneous influence, and it conflicted with later discoveries about the finite speed of information travel. But Newton's equations worked so well that the question was set aside until the 20th century. At the start of the 1900s, Albert Einstein introduced the first of his two revolutionary theories: special relativity. Special relativity showed that nothing travels faster than the speed of light. Time and space are intertwined, and concepts of simultaneity depend on the observer. This framework implied that no influence can propagate instantaneously. That includes gravitational effects. But Newton's gravity implied instantaneous action across the cosmos, a contradiction. This tension set the stage for Einstein's next breakthrough. In 1915, Einstein published his next revolutionary theory, general test theory of relativity. The radical idea wasn't that masses pull on each other, it's that mass and energy warp the fabric of space-time itself. Einstein said, "Matter tells space how to curve, and space tells matter how to move." That's not poetic fluff, it's physics. Instead of gravity being a force that pulls, gravity is the result of objects following the straightest possible paths in curved spacetime. The paths aren't straight in ordinary 3D space, but in 4D spacetime. These paths are called geodesics. Think of spacetime like a stretched membrane. A heavy object creates a depression. A smaller object nearby rolls toward it, not because a force is pulling, but because the geometry directs the motion. In Newton's view, gravity pulls objects. In Einstein's view, objects follow curved paths because space-time curvature guides them. So are we being pulled at all? Not by a force in the traditional sense. Instead, we're following the geometry laid out by mass energy. Free fall is actually straight-line motion in curved spacetime. This was tested and confirmed by Mercury's orbital precession and Eddington's 1919 solar eclipse measurements showing starlight bending near the sun. Both matched Einstein's predictions exactly where Newton's failed. Before Einstein, space and time were thought to be absolute. Space was a fixed stage, time flowed uniformly for everyone. Einstein shattered this idea. In general relativity, space and time are fused into a single entity, spacetime. Spacetime is not just a background, it is dynamic, flexible, and responsive to mass and energy. This is the key shift. Matter does not move through spacetime passively. Matter actively shapes spacetime. When physicists say spacetime is curved, they don't mean it bends into something else. Curvature means the rules of geometry change. Straight lines behave differently. In flat space, parallel lines never meet. The angles of a triangle add to 180 degrees. In curved space, parallel lines can converge or diverge. Triangle angles can exceed or fall below 180 degrees. Gravity, in Einstein's theory, is the manifestation of this geometric deviation. Here is one of the most counterintuitive truths in physics. An object in free fall is not experiencing gravity. If you fall off a cliff, ignoring air resistance, you feel weightless. Your body experiences no force. This is not philosophical, it is physical fact. Einstein elevated this to the equivalence principle. Locally, the effects of gravity are indistinguishable from acceleration. This means standing on Earth feels like being pushed upward. Gravity is not pulling you down, the ground is pushing you up. This alone hints that gravity is fundamentally different from other forces. Electromagnetism has positive and negative charges, can attract or repel, can be shielded, is mediated by particles, photons. Gravity has only one charge, mass energy, always attracts, cannot be shielded, acts universally. Already, gravity looks strange. This distinction is crucial. Other forces act between objects within spacetime. Gravity alters the structure of spacetime itself. This is why gravity resists unification with quantum theory. In technical terms, electromagnetism is described by fields on spacetime. Gravity is described by the metric of spacetime. They are conceptually different layers of reality. At the heart of general relativity are Einstein's field equations. In words, they say the curvature of spacetime is proportional to the energy and momentum it contains. Symbolically, shown briefly on screen for authenticity, GUV equals 8 pi g TUV, where GUV describes spacetime curvature, TUV describes energy, momentum, and pressure. This is not just mass, pressure and energy also gravitate. This explains why light bends near stars, why black holes form, why the universe expands. Gravity is geometry responding to content. Mercury's orbit slowly rotates over time, a phenomenon called perihelion precession. Newtonian gravity could explain most of it, but not all. The missing 43 arcseconds per century baffled astronomers. Einstein's general relativity predicted this exact discrepancy without adjustment. This was the first major victory of gravity as geometry. Reference: Einstein, Annalen der Physik, 1915. If gravity were a force acting on mass, light should not bend. But in general relativity, light follows geodesics in curved spacetime. Even massless photons are affected. In 1919, Arthur Eddington observed stars near the sun during a solar eclipse. The stars appeared shifted, exactly as Einstein predicted. This single experiment made Einstein famous and confirmed that gravity affects spacetime itself. Reference: Eddington, Philosophical Transactions of the Royal Society, 1920. Time itself flows differently in gravitational fields. Clocks tick slower near massive objects, tick faster farther away. This is not theory, it's measured daily. GPS satellites must correct for gravitational time dilation or navigation errors would grow by kilometers per day. Your phone works because gravity is geometry. The Hayfale-Keating experiment, 1971. GPS relativistic corrections, NASA/NIST. In general relativity, space-time is not rigid. It can stretch, compress, and ripple. A gravitational wave is a propagating distortion of space-time itself, traveling at the speed of light. This is not a wave in space-time, it is a wave of space-time. Massive accelerating objects, such as binary black holes, neutron star mergers, produce ripples in space-time that travel across the universe. Newtonian gravity acts instantaneously, has no dynamical space-time. There is nothing in Newton's theory that can ripple. Gravitational waves are a pure consequence of geometry being dynamic. Einstein predicted them mathematically in 1916, just 1 year after general relativity. For decades, even Einstein doubted whether they were physically real or merely mathematical artifacts. On September 14, 2015, the LIGO detectors observed a tiny disturbance, space-time stretched by 1 part in 10 to the 21, caused by 2 black holes merging 1.3 billion light-years away. The signal matched Einstein's predictions precisely. This discovery proved space-time is not static. Geometry carries energy and momentum. Gravity behaves like a dynamical field, yet still not a force. Reference: Abbott et al., Physical Review Letters, 2016, GW 150914. A black hole is not an object in space. It is a region of space-time where curvature becomes extreme, geodesics point inward, escape paths cease to exist. The defining feature is the event horizon, a geometric boundary beyond which all future paths lead inward. Nothing special happens at the horizon locally. Space-time is smooth there. The blackness arises from geometry, not material substance. Once formed, a black hole is characterized only by mass, spin, charge. This is the no-hair theorem. Inside, matter no longer plays an active role. Geometry evolves according to Einstein's equations alone. Black holes are the clearest demonstration that gravity is space-time geometry, independent of material forces. Near a black hole, time behaves like a spatial direction. Space behaves like time. Inside the horizon, moving forward in time means falling inward. This is not metaphorical, it is mathematically unavoidable. Every other fundamental interaction is described by quantum field theory. Gravity is not. Quantum mechanics requires a background spacetime, uses time as an external parameter. But general relativity makes spacetime dynamic, eliminates fixed backgrounds. These two concepts are conceptually incompatible. At extremely small scales, length 10 to the minus 35 meters, time 10 to the minus 43 seconds, space-time fluctuations become violent, and Einstein's smooth geometry likely ceases to exist. This scale is called the Planck scale. Beyond it, geometry may become discrete, or emergent, or replaced entirely. We do not know. Treating gravity like other forces leads to non-renormalizable infinities and predictive breakdown. This suggests gravity is not just another force to quantize. It may not be fundamental at all. Reference: Weinberg, Ultraviolet Divergences in Quantum Theories of Gravitation, 1979. This is one of the most radical and serious ideas in modern physics. The question is no longer, is gravity a force or geometry, but is gravity fundamental at all? In 1973, Jacob Bekenstein made a shocking proposal. Black holes have entropy. This was unexpected because entropy is a thermodynamic concept related to information and microscopic degrees of freedom. Then, in 1974, Stephen Hawking showed black holes emit radiation and have temperature. This implies black holes obey thermodynamic laws. Space-time itself behaves like a thermodynamic system. In 1995, physicist Ted Jacobson made a stunning discovery. He derived Einstein's field equations not from geometry, but from thermodynamics. Assumptions: entropy is proportional to horizon area, and energy flow obeys the Clausius relation, delta Q equals T ds. From this alone, Einstein's equations emerged. This suggests space-time curvature behaves like an equation of state, similar to pressure or temperature. Gravity may be an emergent phenomenon, like fluid pressure, not fundamental. Reference: Jacobson, Physical Review Letters, 1995. Physicist Eric Verlinde proposed gravity is an entropic force, meaning objects move because of information gradients, not because of a fundamental interaction. In this view, space-time is emergent. Gravity arises from changes in entropy. This idea is controversial, but mathematically consistent in certain limits. Entropic gravity is not universally accepted, but it reproduces Newtonian gravity under specific assumptions. For ordinary systems, entropy scales with volume. For black holes, entropy scales with surface area. This implies information about a region of space may be stored on its boundary. This led to the holographic principle. In 1997, Juan Maldacena proposed a precise mathematical duality. A gravitational theory in a volume is equivalent to a quantum field theory on its boundary. This is called ADS-CFT correspondence. Gravity can emerge from non-gravitational quantum physics. Space-time geometry emerges from quantum entanglement. This is one of the strongest pieces of evidence that gravity is not fundamental. Reference: Maldacena, Advances in Theoretical and Mathematical Physics, 1998. Modern research suggests geometry corresponds to entanglement structure. Distance reflects quantum correlations. Space-time may be a manifestation of information relationships. This is active, high-level research. Reference: Van Ramsdonk, General Relativity and Gravitation, 2010. Now we examine an alternative path. Loop quantum gravity proposes space-time is made of discrete chunks. Area and volume have minimum values. There is no smooth space-time at the smallest scale. Gravity remains geometry, but quantized geometry. Space-time is described by networks of quantum states, called spin networks. Geometry emerges statistically at large scales. LQG is background independent, respects Einstein's insight deeply, but lacks experimental verification and does not yet unify all forces. In string theory, fundamental objects are one-dimensional strings. Vibrational modes correspond to particles. One mode is always a massless spin 2 particle, the graviton. Gravity is unavoidable. In string theory, space-time geometry is derived, not assumed. This again suggests geometry is not fundamental. Reference: Green, Schwartz, Witten, superstring theory. Now we can finally answer carefully. Gravity is not a force like others. Gravity is accurately described as space-time geometry. General relativity is experimentally confirmed. What is likely? Geometry may be emergent, gravity may arise from information or thermodynamics. Whether space-time is fundamental, how gravity becomes quantum, what replaces geometry at the Planck scale. Objects pull on each other. Objects move along curved geometry. Modern physics suggests objects and geometry both emerge from deeper structure. Gravity may not be a thing. It may be a symptom. This question goes back to Galileo, long before Einstein. Galileo noticed all objects fall at the same rate, ignoring air resistance. Mass does not matter. This is deeply strange. In Newtonian physics, gravitational mass, how strongly gravity pulls you, inertial mass, how resistant you are to motion, are conceptually different, yet experimentally identical. Einstein saw this not as coincidence, but as a clue. Einstein's equivalence principle states, locally, gravity and acceleration are indistinguishable. But deeper still, gravity and inertia may be the same phenomenon. What we call gravitational force may just be resistance to curved motion. In general relativity, free-falling objects are inertial. Standing still on Earth is non-inertial. You feel weight because you are prevented from following your natural geodesic. This makes gravity fundamentally different from forces like electromagnetism. Proposed by Ernst Mach, inertia arises from interaction with the mass of the entire universe, meaning your resistance to acceleration depends on distant galaxies. This suggests gravity and inertia are not local properties. Einstein was inspired by this idea, but general relativity only partially incorporates it. If Mach's idea is correct, gravity is not a property of objects, it is a relationship between all mass energy. This aligns with relational interpretations of space-time, information-based gravity models, but no definitive experimental test exists yet. Reference: Barbour and Pfister, Mach's Principle, 1995. One of the least understood facts about gravity is pressure gravitates. In Einstein's equations, energy density curves space-time. Pressure does too. This means radiation gravitates, vacuum energy gravitates, stress gravitates. This is why neutron stars are so extreme. Early universe expansion was dominated by radiation. Gravity responds to everything, not just mass. Quantum field theory predicts vacuum fluctuations everywhere, zero-point energy. This energy should gravitate enormously, but observations show the cosmological constant is tiny, 120 orders of magnitude smaller than predicted. This is known as the worst theoretical prediction in physics. Gravity reacts to vacuum energy, but not as expected. The universe's expansion is accelerating. This suggests space-time has its own energy. Geometry is dynamically evolving. Dark energy may be a property of space-time itself, or evidence gravity is incomplete. Reference: Rees et al., Astronomical Journal, 1998, Perlmutter et al., Astrophysical Journal, 1999. Can gravity exist without space and time? Some modern approaches suggest space and time emerge. Gravity exists before geometry. Examples: causal sets, tensor networks, quantum information frameworks. In these, distance is secondary. Connectivity is primary. Gravity becomes a statistical effect. In quantum gravity, time may not exist fundamentally. Dynamics emerge from correlations. This creates the problem of time. How can the universe evolve if time is not fundamental? Gravity may be tied to the emergence of time itself. Reference: Rovelli, Forget Time, 2011. Gravity determines light cones, causal structure, what events can affect others. In this sense, gravity is the architecture of causality. If space-time changes, cause and effect changes. This suggests gravity is not a force, it is the framework within which forces operate. Despite success, general relativity is untested at Planck scales, inside black hole interiors, during the universe's first moments. Upcoming tests: quantum interference with massive objects, precision tests of equivalence principle, gravitational wave polarization. Gravity may still surprise us. Possibilities seriously considered by physicists: information, quantum entanglement, causal structure, computation, symmetry. In these views, matter, space, time, gravity all emerge. Laws are approximations. Even if gravity is geometry, why should reality be geometric? This question has no answer yet. It lies at the boundary between physics, mathematics, and philosophy. Newton: reality is forces acting in space. Einstein: reality is curved space-time. Modern physics: reality may be relations, not things. Gravity has been the teacher every time. for the wandering neuron, and not with answers, but humility. Gravity began as a force, became geometry, and may yet dissolve into information. The deeper we go, the less solid reality becomes. At the deepest level, modern physics is not about forces, it is about symmetries. In 1918, Emmy Noether proved a foundational result. Every continuous symmetry corresponds to a conserved quantity. Examples: time symmetry corresponds to energy conservation. Space symmetry corresponds to momentum conservation. But gravity complicates this. In general relativity, space-time itself is dynamic. Global energy conservation becomes ambiguous. This suggests gravity is not just another interaction, it alters the very symmetries that define physics. General relativity is invariant under smooth coordinate transformations, diffeomorphisms, meaning there is no preferred coordinate system. Points in spacetime have no intrinsic identity. This implies spacetime points are not physical objects. Reality is relational. This is a radical departure from classical physics. Gravity affects not just motion, it affects how measurement itself works. 30.1. Rods and clocks are physical objects. Distances and times are measured using physical rods, physical clocks. But gravity stretches rods, slows clocks. So geometry is not abstract, it is measured by matter that gravity itself influences. This creates a self-referential structure. Gravity defines the geometry used to measure gravity. This is unique among physical theories. In electromagnetism, you can imagine a neutral observer. In gravity, every observer has mass energy. No observer is external. Gravity cannot be turned off. This hints that gravity is closer to a framework than a force. Quantum mechanics insists information is never destroyed. But black holes seem to absorb information, emit thermal radiation, erase details. This contradiction implies our understanding of gravity is incomplete. Either information escapes, geometry must change, or information is destroyed, quantum theory fails. Most physicists believe geometry must give way. This supports the idea space-time is emergent, gravity is not fundamental. Reference: Hawking, 1976, Preskill, 1992. In the Hamiltonian formulation of general relativity, gravity appears as a constraint, not a dynamical force in the usual sense. The equations restrict what configurations of spacetime are allowed. This makes gravity a rule of consistency, not an interaction. Few non-specialists ever hear this. Gravitons are hypothetical, but no experiment has detected one. Gravity may not be mediated by particles at all. In emergent gravity, gravitons are collective excitations, like phonons in a crystal. Phonons are real, but they are not fundamental. Gravity may be similar. Reductionism assumes complex systems reduce to simpler parts. Gravity resists this, because spacetime is not made of spacetime. Geometry emerges collectively. This suggests the universe may not be fundamentally built from objects, it may be built from relations. Gravity governs expansion, structure formation, cosmic background radiation, fate of the universe, yet gravity itself may change with scale. Early universe gravity may differ from today's. Inflation, dark energy, and singularities all point to new gravitational physics. Einstein's equations allow empty solutions with curvature. Examples: gravitational waves, de Sitter space. This means that geometry has dynamics independent of matter. Gravity is not reducible to material interaction. Gravity may be responsible for why time has a direction. Low entropy initial conditions plus gravitational clumping, ergo time asymmetry. This ties gravity to cosmology, thermodynamics, the existence of memory. Gravity is 10 to the 36th times weaker than electromagnetism. This is not accidental. Weak gravity allows long-lived stars, complex structures, life. Some theories suggest gravity's weakness is a clue, not a coincidence. One emerging view, gravity is required for quantum systems to be mutually consistent. It ensures causality, unitarity, and locality approximately. In this view, gravity is inevitable, not optional. Every time we tried to simplify gravity, it became deeper. Every time we tried to reduce it, it expanded our view of reality. Gravity has forced physics to confront time, measurement, information, reality itself. Perhaps gravity is not asking to be explained as a force. Perhaps it is asking us to rethink what explanation means. At the beginning of this journey, gravity seemed simple. An apple falls, a planet orbits, a force pulls. That picture worked, until it didn't. Newton gave us equations that ruled the heavens, yet quietly hid a mystery. How does one object reach across empty space? Einstein removed the force entirely and replaced it with geometry. Objects were no longer pulled, they were guided. Space-time itself became active, dynamic, alive. And for a century, that picture held. But as we went deeper, deeper than planets, deeper than stars, deeper than space-time itself, gravity began to dissolve again. Black holes taught us that geometry has entropy. Quantum theory taught us that space-time may fluctuate. Information theory whispered that distance itself might not be fundamental. At that depth, gravity no longer looks like a push, a pull, or even a curve. It looks like a constraint, a consistency requirement, a shadow cast by deeper rules we do not yet fully see. Perhaps gravity is what remains when the universe demands coherence. Perhaps it is the price reality pays to exist without contradiction. What began as a force became geometry. What became geometry may become information. And what lies beneath information, we do not yet know. And that is not a failure of physics. That is its most honest moment. Because the deeper gravity leads us, the less it tells us what reality is, and the more it asks us how we should think about reality at all. So when we ask, is gravity really a force or just geometry? The most truthful answer physics can offer today is this: gravity is not finished teaching us, and perhaps it never will be.